Once upon a time, a mathematician was listening to a sociologist friend talk about a recent study that he had done on an Indian tribe. And the study was designed to show whether sleeping on different types of animal skins built strength in the women. The skins tested were elephant, rhino, and hippo. The experiment has shown that the women who slept on the elephant and the hippo hides did grow to remarkable strength. The third woman, who slept on a hippopotamus hide, became so strong that she was easily equal in physical strength not only to the two women, but to their sons as well. Upon hearing this, the mathematician remarked to his friend, "Well, I could have predicted that outcome myself." "How is that?" asked the sociologist. "Come now, every first-year geometry student knows that the squaw on the hippopotamus is equal to the sons of the squaws on the other two hides." Sorry. Anyways, that's a Pythagorean theorem joke, which we will be talking about right now. This is a wordless Pythagorean theorem. And what it's showing is you can see the shapes that are equal here. So I have a large square, and the small square has the blue and the green, and the blue and the green are in the large square. And then you have the burgundy and the orange and the yellow are also in the large square, basically saying that the sums of these areas of the two small squares are equal to the sum of the area of the large square, or just the area of the large square. Now, special cases of the Pythagorean theorem were discovered by the Egyptians, the Babylonians, and the Chinese. Pythagoras is the Greek mathematician who showed that the Pythagorean theorem is true for all right triangles. Make sure you get down the Pythagorean theorem, although it is on your math chart. A squared plus b squared equals c squared. Notice that you have two sides on one side and one side all by itself on the other. So the two legs are a and b. Those are the shorter sides. And c is the hypotenuse, the longest side of a right triangle. So to find the missing side of a right triangle, I know this looks really wordy, but it's pretty straightforward. Draw the right triangle and label the sides. It does not matter which side is A or B. The two short sides, we can interchange them and it will always work. C always has to be the hypotenuse, the long side. Then write down the Pythagorean theorem. A squared plus b squared equals c squared, and substitute in the values you know. And then solve for the unknown side. If you're solving for c squared, that's usually pretty straightforward, and you're pretty good at that one. A and b, not so much. You have to remember to subtract from both sides to get the unknown by itself, and don't forget to take the square root once you isolate it. So let's take a look at example 1. The side lengths of the two short legs of a right triangle are 14 and 48. The important thing to know here is we said that we're talking about the short legs, 14 and 48. And we want to find the hypotenuse. So I know I'm going to use the Pythagorean theorem, which is a squared plus b squared equals c squared. And a will be 14 and b will be 48. So I will go ahead and substitute those in. And I will get 14 squared plus 48 squared equals c squared. Then squaring both of those, square them first, don't add them. 196 plus 2,304 will be c squared, or 2,500 equals c squared. But I'm not trying to solve for the squared side. I'm trying to find c. So I need to undo the square. The inverse operation, the opposite of it, is the square root. So I take the square root of both sides, and you find out that c is 50. In this next example, I have the triangle, and I'm going to label the sides. I'm going to go ahead and use A, B, and C. I was tempted to put an X in there, but let's make sure we're putting the right sides in the right spots. So I label A as the unknown side, B is the side with length 5, and C is the hypotenuse, 13. I could have switched A and B, and it would still work out. So I'm going to use the Pythagorean theorem, a squared plus b squared equals c squared. Substitute in. So now I say a squared plus 5 squared equals 13 squared. You can square everything that needs to be squared, except for the a, because you don't know what that is. And I get a squared plus 25 equals 169. I'm trying to solve for a, so I subtract 25 from both sides. And I get a squared equals 144. Not trying to solve for a squared, I'm trying to solve for the sides. So I have to take the square root of both sides. And I get a is 12. Now here we're going to go ahead, and you can see the answer, and find a missing side in the triangle at the right. So same thing, label your sides A, B, and C. You know that the long side is opposite the right angle. See the right angle right here and the 7 over there. So that's your hypotenuse. Go ahead and write down your formula. A squared plus B squared equals C squared. Then substitute in. B I don't know, so it stays as B. A we're calling 5, and C we're calling 7. So I'm going to subtract 5 squared from both sides. And one of the reasons I'm doing this is sometimes your test won't show everything all squared out and subtracted. It might look a little bit like this. But if I was trying to solve for B, I have to take the square root of both sides. So you could say that B is the square root of 7 squared minus 5 squared, or 49 minus 25. And when you subtract those two, you get 24. So B is the square root of 24. So your answer on a test could look like this part right here, or that, or the square root of 24. Now, there's a cool set of triangles called Pythagorean triples. Now, you saw in the previous problem, we had square root of 24. If you put that in your calculator, it's a number just a little less than 5. It's not a whole number. Pythagorean triples are special right triangles where all 3 sides are whole numbers, non-zero whole numbers. So some of the common triples are the 3, 4, 5, the 5, 12, 13, the 8, 15, and 17, and the 7, 24, and 25. If you substitute these into the Pythagorean theorem, they will all work out beautifully. You can create more Pythagorean triples by applying a scale factor. So one example, in this one we worked on example 1 at the very beginning here, that is the same triple as a 7, 24, or 25, except a scale factor 2. Remember, our original sides were 14 and 48, and we found that the last side was 50. So that's as if I had taken all these numbers and doubled them. Now, scale factors are a really great shortcut for finding missing sides on Pythagorean triples. Now we're going to use Pythagorean triples to find missing sides. So one of the things you want to do is pull up the different triples, the 3, 4, 5, 5, 12, 13, 8, 15, and 17, and 7, 24, and 25. Now, if you look at this, one of the easiest things to do is triples should be whole number multiples. So they should be divisible by these numbers. So we're going to find out first which ones are divisible by 12, and which ones 12 are divisible by. And 12 is divisible by 3, but not by 5, 8, and 7. That tells me that my triple is a 3, 4, 5 triangle. And in fact, if I multiply 3 times 4, I get 12. And if I go 4 times 4, I get 16, and then 20. So the 12 and 16 match, and my third side is 20. In this next example, I'm looking at this a couple different ways. One of the ways is I go ahead and write down the triples and eliminate those that won't work. Another thing I can do is simplify this ratio. Now, I'm going to tell you right now that this is the triple that we're going to deal with. But you could have said, okay, I see the 25 goes in there 3 times and the 24 goes in there 3 times. You could have also done a ratio of 72 to 75 and simplified it. And that gives you 24 to 25. Since there's a scale factor of 3 here, then I know just to get this missing side, I multiply 7 times 3, and I get 21. In this triple, I've got 10, X, and 26. By the way, I'm always listing these in ascending order from smallest to greatest. So let's go ahead and write down our triples. And 10 is a pretty good number to look at. So I can tell right away that 3, 8, and 7, 10 is not divisible by either of those. but it is divisible by 5. And in fact, if I multiply 5 by 2, I will get 10. 12 times 2 will give me 24. 13 times 2 will give me 26, which matches there, so that's a good sign. So my missing side is 24. On this last part of this example, I have 18 missing side and 30. Write down the triples again. 5, 8, and 7 do not work with 18. 18 is not divisible by those, but it is divisible by 3. And 30 is divisible by 5. The scale factor for both of these is 6. So I can find the missing side by multiplying all three sides of the Pythagorean triple by 6. I get 18, 24, and 30. I already had 18 and 30. My missing side is 24.